XC equals 1 over 2 pi FC. What is XC? We have R, that's pure resistance, right?
Capacitive resistance?
Capacitive resistance, but it's actually more than that.
Reactance.
Reactance, that's exactly it. Now don't get it confused with impedance. Impedance is really high resistance on the front end from either real resistance, reactance, or whatever. Reactive resistance is purely reactance to the electron flow. What are we doing? We're always controlling electrons, right? So reactive resistance is purely the resistance to the electron flow. And in this case, the only reactive resistance we have is the capacitor. We have a resistor in there, that's pure resistance. The capacitor is the only reactive resistance here, right? Now remember, if we have reactive resistance in the capacitor and the inductor, and we make them equal, we become resonant, and now we just have pure resistance, don't we? Now what really physically is it? Well, in the inductor, it was the buildup of the electromagnetic field and then the back EMF when it collapsed, right? So that was a resistance to flow of electrons, right? Reactive resistance. In the capacitor, it's all about voltage, because in the inductor, it's current flow, right? Always when it's fully charged, it's flowing current, right? In the capacitor, when it's fully charged, how much current is flowing? Big fat zero, right? Flows a little current to charge up, but it's a big fat zero when it's charged, right?
Yep.
Okay, so it's all about voltage. And if we're going to pass AC voltage through it, when it discharges, it does the same thing as the back EMF in the inductor. So now we have a reactance to the flow of an AC voltage through the capacitor, okay? Because an AC voltage will pass through a capacitor. Charges up, boom, 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 okay, through the capacitor. That would be the reactance that we're looking at right there. So we need to be able to calculate that. Okay, so this is reactance here. We'll call it Rx. Okay, so if we look at the equation, well, these are all just whole placeholders, 2 pi, yada, yada, yada. Okay, what's the next thing we see? Frequency. Ooh, frequency has an effect. How? Well, if it's small and we say, we'll just call this a constant for now, we'll just say we had a particular capacitor we're using. So this is stable. The smaller this gets, the smaller this gets, the larger this gets. So more reactance for smaller capacitors? Or for smaller frequencies, I'm sorry. Yeah, and it makes sense. Think of it physically. As we approach the frequency of 0, how much voltage can we pass across the capacitor? 0. I mean, even if it's 100 volts, if the frequency is 0, it charges the capacitor up and we're done, right? So the reactance is low. But the higher we go, the more frequency we have, the more reactance we get out of the capacitor, because the more it will pass, right? And the equation says that. How about the size of the capacitor? Well, the smaller the capacitor, if we just say this is a constant here of a certain constant, the size of the capacitor, the smaller it gets, the more reactance. The larger it gets, the less reactance, right?
Because it can store more?
Let's think about that. A larger capacitor is usually lower frequency, doesn't change as quickly because it's big, right? The time period's pretty long because it takes a long time for those electrons to get in there and get out of there, right? So now our frequency is getting more close to 0 because it can't do it as fast. So what's going to happen? It's going to make a larger reactance, right? Okay. All right, so little tiny capacitors like the ceramics, they're used in high frequency. Electrolytics are used in power supplies, lower frequency, okay?